So in this tutorial, we'll build the equations of Kalman filter in the scalar form. We will take a use case here, and the use case is that we are tracking a stationary car. So imagine a car that is stationary, but it experiences slight position variations due to process noise. And you can consider this process noise as a defective car parking brake, because of which the car is moving randomly because of the effect of maybe wind or slope or something like that. But essentially it is stationary, and there's uncertainty because of the process noise that is getting added because of external forces like wind and slope. So we will use a radar to measure the range of this car, the position of the car. But these measurements from the radar itself are noisy. So we will simulate the noise in the radar measurements. And then we'll use a Kalman filter to estimate the car's true position. So how it works is that Kalman filter operates in two main steps. The first is called the prediction step, and the second is called the update step. So in the prediction step, we predict the next state and its uncertainty based on the current state and its uncertainty. So the state here is the position of the car, and we make an initial guess about the position of the car, which is reflected by mu current. So this is our prior mean of the car's position. And then we make we will predict the variance of the prior, which is as shown on the slide. So we make some assumption about the uncertainty in the car's position, that is the variance in the car position. And then because of process noise, that is the effect of wind and defective parking brake and all, we add that noise into the system, and that's how we get predicted prior variance. And from the first equation we get predicted prior state. So this is the prediction step, and then we move on to the next step, which is the update step. So in the update step, we first calculate the Kalman gain as shown in this formula, which is similar to what we showed a while ago. Essentially, it is the variance of the prior, that is this one that we calculated. And in the denominator part, we add this variance of prior with the variance of measurement. So this is coming from the measurement radar's noise, and this is coming from the process noise. Then we calculate the posterior mean, we update it. So how this posterior mean is updated is using this equation that we saw earlier. So we have initial estimate about the position of the car, which is reflected by mu prior, and then a measurement becomes available, so we get a better idea about the position of the car, which is reflected by mu measurement. So the difference between them is the error, and this error in position is weighted by the Kalman filter gain, which is calculated here, and it is added to the previous estimate, which was calculated here, and then we update the posterior mean. This is how we get the measurement into consideration for the calculation of posterior mean. And now we have to update the posterior variance. So as shown earlier, this can be done by 1 minus k multiplied by the variance of the prior. So and then this whole cycle repeats. We again go back to the next step and predict for the next state, for the next time step, and come back and update for the next time step. So it's a predictor corrector kind of an algorithm, and now we will demonstrate this by implementing it in Python. So in this section, we'll implement the Python code for the car tracking problem that we described earlier. For this purpose, I have imported some libraries. So let's start with that. Now I'm going to define my time axis. So the first step is to define the time step, which is I'm going to be running the simulation in a time step of 0.1 seconds. And let's say the whole simulation should run for 20 seconds. So let's see what this time axis looks like. As you can see, it's just a series of numbers from 0 to 19.9. In fact, we can correct it and take it to 20 seconds by doing this. So now we get 20. So the time axis has been created. So our first step now is to simulate the true motion of the car. And as we know, the car is static, it is not moving. Actually, it's not supposed to move. So let's say the true position of car is at 0 meters. And now because of the action of wind and slope, and because of defective parking, this car is moving, rocking back and forth. So we call it process noise, and let's simulate this process noise. So let's say this the sigma of this Gaussian distributed noise is say 1, and the mean is 0. And we define a Gaussian probability distribution, which has got mean, which is 0 here, and sigma, which is 1, and it is as long as the time axis, which is 20 seconds. So and then we take the true position of the car and mix it with the process noise to generate the noisy position. So let's plot the noisy position of the car. Let me just activate my plots here. And what essentially I'm doing here is that I'm plotting the true position of the car, which is static at 0 meter, and then I'm plotting the noisy position of my car. So let's run this code. and here we are. So what we see here is that the time axis is from 0 to 20 seconds as we rightly defined it, and our position is in meters here, and this is the 0 position, and this green dashed line shows the true position of the car, which is ideally speaking should be at 0 meter. But since due to the action of wind and uneven slope, this car is moving back and forth, so these orange lines, they depict the noise in the movement of the car or the position of the car. So that introduces randomness in our system. Then we are going to define the noisy radar measurement, exactly the same way the way we design the process noise. We are going to design the radar noise. Essentially, a radar is measuring the position of the car, but the radar measurements themselves have a lot of noise. So the sigma of that noise is, that is the standard deviation of that noise is 1.3, and it's higher than the process noise, and its mean is 0, and it is Gaussian distributed. So here I have defined that this is Gaussian distributed. So I specify the mean, I specify the sigma, and I specify number of such points I want. So I want it for 20 seconds as long as the time axis is, and then I'm going to take my true position of the car and I'm going to mix radar noise with it, or the measurement noise with it, to make it corrupted radar reading, or the radar's version of the position of the car. And then I'm going to just plot all three, that is the true position of the car, the noisy position of the car, and the radar measurement of the car. So let's see how it looks. So in this figure, the green dashed line is the true position, the orange line is the noisy rocking motion of the car because of wind action, and what we see here as these dots, red dots, are actually the radar measurements. And as you can see that it's pretty noisy, it's more noisy than the back and forth motion of the car itself. So this is what is the input to the filter, and if everything works well, then this Kalman filter should be able to track the true position of the car as closely as possible. So practically speaking, what the filter is going to see is this. Yeah, so this is what the filter is going to see. As you can see that the car is, the measurements are quite noisy. Here it is 2 meters, then it goes to minus 1.2 meters. At some times it is minus 4 meters, and at some times it is plus 4 meters. So you see there's a lot of noise in the radar measurement. And from these measurements, the desire is that the filter should be able to track the true position of the car. So I'm going to enable these plots once again. So as we discussed earlier, there are two steps to the Kalman filter. So our next step is to design the Kalman filter, and the first step is to design the predict step of that Kalman filter. So we have to start with the initial estimate or initial guess, which is what is this mu current is. Mu signifies the mean position of the car. So we make some educated guess about this position, and that becomes our mean of the prior. And then we predict the variance of the prior, and we calculate the variance of the prior by this equation, where we have made some initial assumption about the variance of the initial variance of the position of the car, and then we mix it with the variance of the process noise, and that becomes the prior variance at the predict step. So now we have priors available to us, and now we have to take into account the likelihood. The likelihood, as I said earlier, comes from the radar measurement. So we have to then, once these priors become available to us, we have to then design the Kalman filter and take into account the likelihood part. So as discussed earlier, the Kalman gain is to be calculated first, and which is by taking the ratio of variance of prior divided by variance of prior, and this variance of prior has come from here, and adding it with the measurement variance, that is the noise variance of the radar. And this part does take into account the radar measurement, which is the likelihood part of the Gaussian product. Once we get the Kalman gain, then we calculate basically posteriors. So mu posterior, that is calculated using this equation as shown on the screen. Essentially, we are taking the radar measurement and we are subtracting our previous belief, which gives us an error in the position of the car. Then we multiply by Kalman gain, and then we update our position. And then we update our posterior variance using these equations. So let's implement these in code. So firstly, we have to start with some initial guess, that is mu current and sigma square current. So I define mu current as say 0, and say these are pure guesses. There's no scientific theory behind it. These are initial guesswork. And then I initialize 3 empty lists to store the outputs of my Kalman filter. So I have a mu posterior from here, I have a sigma square posterior, and I have a Kalman gain which I would like to track. So for that, I have defined these 3 empty lists here, and now I start the design of the filter. So for each radar measurement, I have to run this filter. So all my radar measurements are in measured positions, which is, as you see here, which was nothing but true position added with the measurement noise. So all my measurements are here. So I'm going to loop through each and every radar measurement and run these Kalman filter equations. So the first step is my mu current becomes my mu prior, and my sigma prior squared, actually this is variance, is implemented using this equation, which has come directly from here, this part. So, and the first one is from this part. So this is what is implementing the predict step, and then we go to the update step. So in update step, we calculate Kalman gain, and Kalman gain is nothing but what we have calculated here. That is the sigma square of the prior divided by sigma square of the prior plus the sigma square of the measurement or the radar noise. And actually you can see this is exactly what is given here. And the next step is to calculate the posteriors. So firstly, mu posterior, that is mu is nothing but the position of the car. So this is a posterior position of the car, which is implemented using this equation, which is exactly what is given here. And this Kalman gain has come from here, and measurement is coming from the looping through of all the measurements that is given in this list. So that's how we can calculate the mu posterior, and then we have to update our sigma square of the posterior, that is the uncertainty of posterior, using this equation. So as you can see, this is how it is done: 1 minus Kalman gain multiplied by sigma square of prior, which is sigma square of prior. So we get sigma squared of posterior, which is nothing but variance of posterior. And then in the next step, because there are so many measurements, for each measurement I'm going to store the filter output. So I'm going to save all these values in my lists that were defined here earlier, these empty lists. So all these values will get stored here. And then for the next step, my mu current, which was defined here, gets updated because now I have posterior available. So my posterior at this step becomes my current, and again the sigma posterior becomes sigma current, and they in turn come back to this step, and this whole loop executes again and again and again, which essentially is what is Kalman filter all about. So predict, update, and then go back here and plug these values in mu current and sigma square current, and keep running this loop as for as many measurements as you have in the measurement position array. So and then I'm going to print out these parameters, and also I'm going to calculate the Kalman gain, print out the Kalman gain, and then do some basic plotting regarding the filter outputs and probability density functions and Kalman gain. So let's run this. Wonderful. So let's start from the first output. We know that as far as true position of the car is concerned, it is static at 0 meters, so mu is going to be 0. And since there's no perturbation, it's a true position, there's no uncertainty, so sigma is also 0. Then we add the process noise, that is the action of wind and uneven slope. And we had defined our sigma, our mu process noise as 0. So you can see it's very close to 0. And our process sigma was close to 1. So here it is 0.96. You can see it from the settings done here. Here. So 1 and 0 are coming from there. And if you note the 1.3, that is sigma for the radar, and mean of the radar noise is coming from here, that is 1.3 and 0. So here we are. This is the output of the radar, which is the mean of the position is very close to 0, and the sigma of that position is 1.35. Now, as per Kalman filter theory and as per the Bayesian filter theory that was explained earlier, these two are getting these two standard deviations after they get passed through Kalman filter. The end result should be lower than both of them, and that's how we defined the Bayesian filter earlier, which is a product of two Gaussian. So if you actually see this 0.94 is lower than this 0.96, and it's also lower than 1.35. That means the output of the filter is lower than the standard deviation of the output of the filter is lower than both the process noise as well as the measurement noise. And actually you can see here, as explained earlier, these red dots are radar measurements. The orange one is noisy position. Green line is the true position, and this blue is the output of the filter. And as you can see, it is not having as wild a fluctuation as these radar measurements are having. In fact, a very few of these peaks are crossing 2, and a lot of these radar things are crossing 2, plus 2 and minus 2. And then we see the PDFs. So if you see, red is the PDF of measurement, that is the radar. So it's since the radar noise is very high, its PDF is centered at 0 but very flat. The uncertainty is high. And then we have process noise. Its standard deviation is lower than the measurement noise. If you remember, it was 1. So it is peakier and still centered around 0. And the product of these two Gaussian PDFs, as explained in Bayesian filter theory, should lead to a standard deviation which is lesser than both. So this is exactly what is happening. This is the filter output, and after combining the noisy position and the noisy radar measurement, thus uncertainty in the system is reducing because we are using the basin filter theory, and that's the reason why this PDF is very peaky. So essentially speaking, the Kalman filter is trying to reduce the noise from the system or reduce the uncertainty from the system. Lastly, we see the Kalman gain. So if you have noticed, we started with the initial guess of mean 0 and sigma 0.5. These are just pure guesses. So Kalman filter takes some time to converge to the right values, and at that point the Kalman gain gets fixed. So as you can see, as the time is passing by, Kalman gain is getting adjusted, and after a while, in fact after very few steps, in fact just about in 0.4 seconds, it reaches stability, and the end Kalman gain is somewhere around 0.5 slightly higher than 5.2. So that's how things work, and I hope you have understood the entire theory. We can actually play around with this, and what an interesting case is that if both the sigmas become equal, so what we can do here is that let's say my process noise sigma is 1, and my measurement sigma also becomes 1. So let's run this. So you see something very interesting happens. My filter output is exactly the half of both these PDFs, and it is becoming very peakier here. That means the noise from the system is getting removed. In fact, we can see we can take more number of sample, and you'll be able to see this clearly in time domain. So for that, what we can do is we can increase the time axis, which is here. So instead of 20 seconds, let's say 500 seconds. Now you can very clearly see what's happening here. So the radar's measurement has very wide fluctuations, is fluctuating very wildly because of noise. And then we have now process noise, which is also wildly fluctuating as badly as what the radar is doing, which is what is shown by these orange lines. And this bluish plot is the output of the filter, and you can see that it is quite centered around the true position of the car, which is 0. And it is not fluctuating as wildly as both the radar measurement as well as the process noise, indicating that the Kalman filter has been able to act as an optimal combiner, and because of that optimal combining action, the noise in the system has got reduced. So that's all for this video. We'll make another Kalman filter for the moving car version.